Welcome to the section on modeling. We shall be looking at the recurrent neural network. Previously, we had seen deep neural networks and convolutional neural networks. Now, generally, when solving problems in which the data we have comes as a sequence, we tend to use recurrent neural networks. We had seen previously that when given an input sentence, say, I like this movie, then we break that input data into different one-hot vectors, where each one-hot vector represents one position of that sequence. So instead of just taking the input data and passing this kind of deep neural network with this one hidden layer and obtaining an output, we are going to stack this deep neural networks such that each of them represents one element in that sequence. So if I want to consider an input sentence like I love this movie, we'll have maybe the start, which passes here, I love this, and then finally movie. So if the sequence length is, for example, 100, we're going to have 100 of these different deep neural networks. Now, how are they connected together? You have that in between these neural networks that's linking the different hidden layers, we have some other neural networks. So this neural network goes this way, we could come back. So we have this neural network which takes this input and then with this hidden layer and this output. Now we can connect this hidden layer to the next hidden layer, and then this to the next hidden layer, and this to the next hidden layer, and so on and so forth. So we see that this actually makes it possible for information to travel from one neural network to another via these hidden layers. And so this global neural network will take decisions more efficiently, since even with the data, the positioning of each word or some of the words actually affect or give more meaning to other words depending on their positions. So we see that with recurrent neural networks, this problem of solving problems in which our input data is in the form of a sequence or is distributed over time becomes very easy. Now, so we're supposing we have time t equals 1, t equals 2, t equals 3, t equals 4, and then say t equals the sequence length, and then we have this different weights, where the weight which links a hidden layer in the previous neural network to the hidden layer in the current neural network is WHH, since we went from one hidden to another hidden. And then this other weights which link the input X, which is this input X, to the hidden layer is HX, hidden X. And then this other weights which link the hidden to the output Y is hidden Y. So we have YH right here. So basically, these are the kind of neural networks we had seen previously, with the difference that they have been linked together via this other network which connects their hidden layers. Now, to obtain each hidden layer, as you can see clearly here, we have WHH times a previous hidden layer. So if we add time t, that's HT, we have WHH times HT minus 1 plus WHX times XT. So we have this input X times WHX, which gives us this value, plus WHH times HT minus 1, and that's what gives us this H. Now obviously we include the bias, so that's how we obtain this H, which is the hidden layer. Now to obtain the output layer Y, we have Y is equals WYH times the hidden layer. So now this is some sort of input for this output. So we have this WYH times the input plus the bias. Now this A1 and A2 are simply activation functions. So they could be a tanh function, sigmoid function, but generally with recurrent neural networks, we work with a tanh function. So that's how we look at this type of neural networks. And so when our input data is of dimension batch size, by sequence length, by vocabulary size, it simply means each of these represents one value in the sequence length. And then for each of these values, we see that we have this input which takes in our 1 hot vectors. If you could count this, you have 19 as we had in the previous example. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this is our 1 hot vector which is passed. So we pass this 1 hot vector for the next value. So if we have, for example, I love this movie, we have start past I love this movie. Now that's basically it. And then we have obviously the batch size, since we may want to treat the data in batches and not just single data points. Now this isn't the most common way of representing neural or recurrent neural networks. In many times in literature, you should have this kind of notation, although this one actually clearly shows you what's happening under the hood. So right here we have each of this box, which is basically just one of this deep neural network. We have the input x1, that's when time t equals 1. We have the h0, that's the hidden layer, an input, an initial hidden layer which may be initialized to zeros. So we could consider our input here as some value zeros. So basically here you have 0, 0, 0, 0, 0, 0, which is here. And then we have this box which collects this input hidden, collects the input value, and then outputs the y. So what exactly happened in this box is what we've just explained right here. And then here we have this output. What's outputted here is this hidden layer. So it's basically this. So what we have here is h1, which is what we get right here. So the values we have at this layer is h1, and that's what we use to obtain h2, and then to obtain h3, and then to obtain h4, and so on and so forth up to h sequence length. So that said, we could now see how we obtain the y's. So the y is right here, and so on and so forth. So basically this is a more simplified way of rewriting what we had seen previously. But what's important to note here is that with recurrent neural networks, we are able to model sequences more efficiently. Now in this our problem, we're trying to take in some inputs and then say whether that input or those input words or that input sentence is a positive or a negative review. So we need to rearrange, or we need to modify this model again. So with this, we'll have that we could design, or we could add some neural network again which collects these 4 points in the output. Now note that these 4 points were just arbitrarily chosen, so the number of output values actually depends on you. So here we have this 4. What we could do is we could actually use a neural network to obtain this 4 output, or we could just flatten this outputs. So we see that for each time step we have this 4 output here, we have this 4 output, we have this up to this, right up to the end. Now this has been somehow flattened. So as we saw, we could use a flattened layer, or we could use a neural network to flatten this out. And then once we flatten this out, we take this as an input to another neural network. So this is an input to another deep neural network, this single deep neural network, which has only one output, which is logical since we are either saying that the input sentence is a positive or is a negative review. Hence the reason why our output has just takes just one value. So in this case, once we have our inputs, we have the outputs, and then we can train this end to end. And after training our model, we could test it and see how well it performs. So basically that's how we kind of model this kind of problems. Let's now see how to implement this recurrent neural networks practically. Before building the whole recurrent neural network, we shall start by building an RNN cell, that's a recurrent neural network cell. Basically, this represents a recurrent neural network cell. And it's by combining these cells that we obtain a recurrent neural network. Note that a recurrent neural network is characterized by the hidden layer size. So in this case, we have a hidden layer size of 7, output layer size, which we shall note as the number of units, which in this case is 4. So that's how right here we define this units and then the hidden size. So we have our units, which represents the number of output neurons. So number of output neurons, and then the hidden size, number of neurons in the hidden unit. And then we have the build function, which contains the different trainable parameters. We have WHH, WHX. WHH links the previous hidden layer to the current hidden layer. WHX links the input to the hidden layer, and WYH links the hidden layer to the output. So these are the different parameters which we train. And then we have the biases. So here we have self.addWeight. We define the shape, we initialize them, and then we'll say whether they are trainable or not. Now notice that this shape can be gotten very easily, as HH defines the hidden size. So now this hidden size, if it's equals 7, is because the previous hidden unit dimension 7 or has 7 neurons, and then the current hidden unit has 7 neurons. So that's why the shape is 7 by 7. In this case, HX, if we suppose that we have an input like this with this kind of shape, so we have the byte size, we have the sequence length, which we could just take to be 100, and then we have the vocabulary size to be 2000. Then this input, because we have this input right here, this input shape will be this. And now input shape -1 will give us 2000. So right here we have 2000, or we could, let's modify this, let's take this to be 19 as we had in the example in the slides. So here we have 19. So right here we have 19, and then the hidden size, as we had seen, here we have 7. So, and as you can see right here, this neural network, which is this, linking the input to this hidden layer, obviously should have weights of dimension, the number of input neurons by the number of hidden neurons. Now the number of input neurons here is 19, and the number of output neurons is 7. And that coincides with what we have here. So let's go back, and we have this. Okay, so there we go. Now for YH, we are linking the hidden to the output. Now the units represents the number of output neurons. So basically that's it. Now for the bias, we have the hidden size, since this is for H, and then for the bias or BY, that's for the number of units. So that's it. So that's how we declare these parameters, and then in the call function we explicitly show what happens in this recurrent neural network cell, or in this singular recurrent neural network path, or via one time step. So right here we have H and Y. We have seen these formulas already. This is the activation function A1 and A2 we had defined previously. So right here we have H previous, that's where we had HT equals the activation of the weight times H previous. So this is HT minus 1, which is H previous, plus the weight HX times X plus the bias. So this gives us what we have right here. So we could easily understand this from the formula we had in the slides. So that's it basically. This is our X, the inputs. This is our WHX, and this is our BH. And then to obtain the output y, we have h, which is this, times wyh plus this bias by. And then finally we convert this to tensors and output this in our call. So basically that's our recurrent neural network cell. So we could run this now. We could define the output, or rather the inputs, which is this 0 vector dimension, the batch size by the vocab size. Now we're not considering the sequence length right here because our sequence length is 1. So basically this is our input. And then we have the layer, which is the RNN cell layer, which we define here. RNN cell as a unit 4, hidden size 7. Now since it's 4, we don't need to define that. We could take that off. And then we have this output h and y, which we're gonna see these shapes from here. So we run this, run that, and there we go. These are the shapes we obtained. For h we have 8, 7, and then for y we have 8, 4. Now this 7 is because the hidden size is 7, and then for the output we have 4 output neurons. So this works just fine. Now let's see how we're gonna join this or make use of this RNN cells to build a full-fledged recurrent neural network. Now to build this recurrent neural network, we define the RNN cell, which we just had right here. So basically we define this RNN cell and we give it its units. So here we're supposing that the hidden size is 7. So we just have this the hidden size here. The hidden size here is 7. So we're not going to define that explicitly. So we could always define it, but right here we just define an RNN cell with hidden size 7, which is actually the default hidden size. And then we have the number of units which we shall define, or which we shall come from the definition of the RNN. So when we shall define this value we shall get from here. So that's how we define this RNN cell. Now in the call function, what we shall do is go through the RNN cell a given number of times, because basically the RNN, or the recurrent neural network, is formed by looping through or repeating the RNN cell. So we shall just simply go through this RNN cells a given number of time and then generate the given outputs. So let's look at this in depth. Now the outputs, this is a list containing the different outputs at each time step. So that's it. We have these different outputs at each time step, and then for the very first time step we shall define, or we shall get the output h, or the outputs h and y. So the hidden output and then the actual output y. And this is done for the time t equals 0. So when we suppose that when time t equals 0, because basically this inputs of the form batch size, so it's important we note the form in which the inputs come in. The dimensions batch size, we have the sequence length, and then the vocab size. So in this case we have 8, we have, for example, 2000. No, rather we have 100. So we have 100, and then we have the vocab size of 2000. So we shall go through each of these time steps. Now note that at the level of this RNN cell, here we had gotten this h previous, that's the previous h. Now initially the h previous is gotten by initializing this array, or this tensor of dimension batch size number of hidden neurons. So basically when we're just starting off for the very first RNN cell, the h previous is gotten from this, but for others the h previous is actually gotten from this one. So it's logical here that when we start off we don't have any h previous which is passed into this RNN So as you could see right here, there is no h previous which is passed. Yeah. So we have no h previous which is passed. So when there is none that is passed, what we do is we take this 0 matrix, and in this case, as you could see, the initial or the input or the h previous is initialized to the 0 matrix. So when we do this call, our h previous here, our h pref is actually equals none. So that's it. Now once we've done this and we've gotten these outputs h and y, obviously since the y's form the outputs, because the output is gotten by joining together all the different y's. So this outputs in this, for this output or this list, we actually add up. So we add up y to the outputs. So this is like our first y, or for our time step 1. Now for the rest of the time steps, that's why we start from 1 right up to the end. For the rest of the time steps, what we'll be doing is we'll be taking the outputs. So like this h is going to be used right here. So instead of this case where we use an h previous of none, such that we initialize it to a 0 matrix, here we're going to use the h previous from the previous RNN cell. So in that case, in this case, we're not going to pass through this. We're just going to take the h previous, which is going to come from the previous RNN cell, so the h that we have here. So that's it, and it's going to be used now to calculate h and subsequently y. So that's how it works. So with this, we go from I in range 1 right up to inputs shape -2. Now -2 because we're going through the sequence length, and this is -1, -2. That's starting from the right to the left. So we are basically saying we're going from 1 to 100. So that's what we are doing right here. We're going from a 1 to 100 because from 1 to the sequence length. So that's it. And each time we do this, we take the h and we repass it into the RNN cell, and then we take this y and we add it up, add the y to the outputs. So that's it. Now once we're done with this, the output we get from here, so let's print out the output.shape. So let's print this out and then try to define some inputs from here. If we do this, we have this batch size, we have a sequence length of 100, and that's it. We define this RNN, which takes in the number of output units. So in this case, let's say we have 4, and then here we have, let's say, the outputs. So let's print out outputs.shape. Okay, we'll run this. RNN not defined. We'll run this from here. What we told has no attribute shape. Outputs equals layer input. Okay, we try to print this out. It had no attribute shape. We have this. Okay, as we could see from here, we have the shape 108.4. Now this is telling us that we have the shape batch, or rather sequence length, because the outputs is being, or the outputs take in this y's. This y's are of dimension batch size by output size, or by number of units. So we have batch size by number of units, and we go through each part of the sequence. So at the end, we have this array of dimension 100 by 8 by 4. But actually, the way we want our dimensions to be is instead the batch size before the sequence length. So for that, we just basically reshape this while considering the shape of the first, that's this 100, by swapping this position with the 0th and maintaining this one at the second position, which is this 4. So when we do this, we have this output now. So let's take this off, rerun it again. So basically, that's how we get this output 804. So for each batch size, or rather for each data point, and for each of the time steps, we have outputs of 4. Now we've seen how to build this from scratch. Let's see what TensorFlow has to offer. We shall see that with TensorFlow, all we need is just this. So we have this tf.keras.layers simple RNN. So basically, let's go back. So we have tf.keras.layers. So we could do this from TensorFlow.keras.layers, import the simple RNN, run that, and we're fine. Okay, so let's do this. Now we have the simple RNN, which we could define as layer, as we had just previously. We have this layer, we have the inputs. Let's take this from here, put this right here. We have this inputs, we have now the outputs. Outputs equals layer of the inputs, and then we print out the outputs ship. Now we have this value because the number of units as we had defined was actually 20. So this is to tell you that this is the number of units or the number of output units. So I have this 4. See, we have the same kind of output. Now let's look at this. This activation here is tanh to tell us that unlike with what we just did, that's we just fixed this to be tanh, we could actually take this activation in parameters such that this could be modified to be sigmoid or whatever activation we may want to work with. So that is good for this. Use bias true to say whether we're going to have this bias parameters to be taken into consideration, and then the return sequences to be true. That's to say whether the output should be a combination of all the different outputs in each time step or just the output in the last time step. So let's modify this. If we have this to be false, for example, run this, you see we have this 84 telling us that is just the very last output we're considering. So instead of returning, so when we have return sequences to be true, we're taking this, this, and finally this output. That is, we're putting all this into a list. But when it's false, we're just collecting just this last output. And depending on the way you want to model your problem, instead of doing it as we just saw, that is by having this, that's by having this neural network getting each and every value from each and every time step, we could just collect this last one and build a small neural network which will have an output of 1, or which will have an output with 1 neuron in the final layer. So basically that's how we could also approach this problem. So that said, we've seen how we could build a simple recurrent neural network with TensorFlow, either from scratch or using this which has been built already. Now we've defined a recurrent neural network, and we can go ahead to build the full complete model. So with this, we have the inputs. That's the input layer of shape, sequence length, vocab size. And then we define the sequential model. So we have the sequential model which gets the inputs. It then gets the simple recurrent neural network with 20 output neurons. So that's it. And then with the 20 output neurons, we have this dense layer. What this dense layer does is, for each time step, it passes a dense neural network which outputs, or which has an output of 1 neuron. And then from all these different outputs, we shall reshape them and then pass again through another dense layer with output 1, and of course of activation sigmoid, since we're having a binary classification problem to solve. So let's run this, and there we go, we have these results. So we have 40,000 parameters to train. And then let's look at the outputs. So we have the batch size 120. So it's similar to what we had here. So let's put here 20. See that we should have that same output. So that's it. So we have the batch size, the sequence length, the vocabulary size. Now once we have this, each of these outputs is passed via a dense layer. Now you have been used to working with a dense layer with this kind of input. So let's take for example, let's just define this, or let's have for example dense. Let's call this dense. So we have dense, which is basically this layer. So we have this layer. Okay, so we've defined this as dense, and then dense takes in an input. Let's have this inputs equals, let's just take this input. So we have this input, and then we have dense of the inputs, which is the outputs. We can now print out the output chip. Okay, so we have this. Now we have this inputs, we have the dense, we have the output, and then we'll print this out. Let's run this, and we have this output chip. So as we were saying, generally we're used to having just this. We're used to having just the batch size with the inputs. So this is what we've been seeing already throughout this course. So we have the batch size, the inputs pass through a dense, and we have an output. So this converts this 100 input to this one output. Now what happens with this is that when TensorFlow gets an input of dimension 3, it kind of produces a time distributed dense layer, such that we have a dense layer for each time step, and that's why we have this kind of output. So what we're actually saying is, for each of these outputs from the recurrent neural network layer, we have the dense layer, which converts this 4 neuron output into a 1 neuron output. So in this case, we'll not be using this, but instead this one, where the output number of neurons is just 1. So we have the dense layer, or a single dense layer, which takes this and outputs this 1. This dense layer takes this, outputs this 1. This takes this, outputs this 1, and so on and so forth for each and every time step. Call that the number of time steps we have here, actually 100 in number. And since the shape here is the batch size by the sequence length by 1, we could reshape this very easily into this. So we take this off, and then we use this as input. So we are gonna have now or build a dense layer, which we take this as input and have this output. So that's how we actually model this problem. And another possibility, as we had seen, would be to take this, for example, to be false. So if we have this to be false, we'll see that that difference come out very clearly. Here we're already having an error because of the incompatibility in the dimensions. So we could see the total size of new array must be unchanged, input shape, output shape this. Okay, so let's go step by step. Let's take this off. Could just simply take this off. Let's take this off. Run this again. You see the kind of output shape we have this time around, and that's because we are just taking the last output and not all the outputs throughout the whole time frame, so or throughout the whole sequence. So once we have this, we could now build simply a dense layer. So we could take this, uncomment this. We could build a dense layer from here and build this kind of simple model. You see that it works just fine with this kind of model. So you could do this or do what we just previously used, but what we shall use in training is this one. So we'll take back. Okay, so feel free to play with this model and see the kind of results you could obtain by changing or modifying the way the model is designed. Okay, so finally this is the model we'll be using, and see you in the next section.